In the last video, we talked about two types of transformations, the translation and the reflection. In this video, we're going to talk about another type of transformation called a rotation. And a rotation is a transformation in which the figure is turned around a fixed point. So this is a rotating of a shape, not a slide or a flip. So we can rotate a shape. So if you see in this picture, we have this flag. And when you rotate something, it rotates around a point, and that point is called the center of rotation, the point around which a shape is rotated. So if you can imagine putting your finger right here on this point A and then rotating that, where your finger is called the center of rotation. So we're going to talk about different types of rotations. We're going to talk about 90 degree, 180 degree, and 270 degree rotations, both clockwise and counterclockwise rotations. So how do you rotate something? So let's look at some rotations that we have here. This first one is an example of a 90 degree clockwise rotation around the origin. So we're going to use the origin in this example as our center of rotation. So if you can imagine putting your finger on the origin and then rotating the coordinate plane or rotating this figure 90 degrees clockwise, and I'll try to show you that here. So if you could imagine this blue shape, we're going to rotate it 90 degrees clockwise, boom, we land right there on the green image. So I have the new coordinates of the image plotted below. So what happens to our ordered pairs when we rotate something 90 degrees clockwise? You can see we started with point A at 1, 1, and it rotated to the point 1, negative 1. Well, it's kind of hard to tell what happens because they were both 1s, but look at point B. B started at the point 3, 4 up here, and then when we rotate it, it ended at the point 4, negative 3. And then likewise, the point C started at 3, 1, and when we rotate it, it ended up at 1, negative 3. So what's happening to the coordinates when you make a 90 degrees clockwise rotation? Well, the points, the ordered pairs, are actually reversed. They're flipped. So like 3, 4 became 4, 3, and 3, 1 became 1, 3. And not only that, the y value became opposite. So there's kind of a complex thing that's happening here, but if you can keep it straight, it's really not that hard to perform this rotation. So the points were flipped and the y value became opposite. Okay, that's what happens when we made a 90 degrees clockwise rotation around the origin. Let's take a look at a 180 degree rotation around the origin. Again, we're still using the origin as our center of rotation. So we're going to rotate around the origin, and we're going to rotate it 180 degrees. So what happens when we go, there's 90, and here's another 90, boom, 180 degrees. So what happens to the ordered pairs when we rotate a shape 180 degrees around the origin? So again, we had 1, 1, and then ended at negative 1, negative 1. And then B started at 3, 4 and ended at negative 3, negative 4. And C started at 3, 1 and ended at negative 3, negative 1. Well, hopefully this transformation, this rotation, is a little bit easier to tell what's happening. The points don't get switched, or the ordered pairs don't get switched, but they both become opposite. Just make everything opposite and plot those points, and then that will create a 180 degree rotation around the origin. So a 180 degree rotation is pretty easy to do. And then finally, what about the 270 degree rotation clockwise around the origin? Again, we've got 90 degrees, 180 degrees, and then 270 degrees. What's happening to our ordered pairs when we make a 270 degree rotation around the origin? Well, again, our A point started at 1, 1 and then became negative 1, 1. The B point started at 3, 4 and became negative 4, 3. and then the C point started at 3, 1 and became negative 1, 3. So again, just like with the 90-degree rotation, the ordered pairs are reversed. They're flipped. But now instead of the Y value becoming opposite, it's the X value that becomes opposite. So really there's some nice symmetry here between how we perform these operations. So you flip the coordinates and the new X value becomes opposite. And I'm going to have those on the next slide, a summary of those points so you can write those down. But that's clockwise rotations. What about counterclockwise rotations? How would we get something to turn the other direction? Well, fortunately, it's the same, almost the same stuff. Let's take a look at this 270-degree rotation again. This was clockwise. Here's a 270-degree clockwise rotation. But what if we were to take this shape and rotate it 90 degrees counterclockwise? It's the same exact thing. So a 90-degree counterclockwise rotation is the exact same thing as a 270-degree clockwise rotation. So you would do the same thing. So really we don't have to learn a new rotation. We just know that those two rotations are actually the same. And then with the 180-degree rotation clockwise, what would a 180-degree counterclockwise rotation look like? Well, if we go this way, 90 degrees, 180 degrees, it's the exact same thing. So a 180-degree rotation is the same, both clockwise and counterclockwise. You end up in the same place. So you only have to remember a 180-degree rotation. It doesn't matter if it's clockwise or counterclockwise. And then finally, the 90 degrees clockwise rotation would be the same as a 90, 180, 270-degree counterclockwise rotation. So these two rotations are identical. So that pretty much covers all of the 6 types of rotations that you can possibly have around the origin. So here are the directions for how to make a rotation any direction and the different degrees that we're talking about. So let's try it. Rotate this figure 90 degrees clockwise around the origin. So performing a 90 degrees clockwise rotation, just a quick review, 90 degrees clockwise, you have to reverse the ordered pairs and then make the new Y value opposite. So what will our J prime become? Well, if I reverse the ordered pairs, I get 2, 3, and if I make the new Y value opposite, it becomes 2, negative 3. Which would be 2, negative 3 right here. That's where J prime is going to be. And if I reverse the ordered pairs in K and make the new Y value opposite, that puts me at 7, negative 6. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. That is going to be my new K or K prime. And then L, I reverse the ordered pairs and make the new Y value opposite, 4, negative 8, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8. That is my new L prime. And here is my triangle rotated 90 degrees clockwise around the origin. Now, the other type of rotation that we're going to do is rotating around a point other than the origin. What if I wanted to rotate it, but I didn't want to use the origin as my center of rotation? What if I wanted to use one of the vertices of the shape to rotate it around? Well, this is a little bit more complex. So we're going to do it in 2 steps. We're still going to perform the rotation around the origin. We're going to rotate it around the origin like we would, but then we're going to take the shape and we're going to perform a translation. We're going to slide it into the position we want. We're going to move the shape to the center of rotation that we want. So here's an example of how we can do that. So what we were asked to do is rotate triangle ABC 180 degrees clockwise about vertex B. So this original blue triangle, we want to rotate it around not the origin, but we want to rotate it around point B. Right here. We wanted to rotate it around point B. Well, the first thing I did was rotate it just 180 degrees around the origin, and I got the green triangle. So after I rotated it 180 degrees, I got these ordered pairs right here and this triangle right here. So I rotated it 100 degrees first, and then secondly, I need to perform a translation. I need to move this shape so that B matches up with where B started. Because if I'm rotating that original triangle around vertex B, B isn't going to move. So I need to put B back on top of B where B was before. So to do that, all I have to do is count the number of spaces that I need to slide this thing. So I need to move it up 6 units and right 6 units to get it back where it was. And that's what I'm doing right here. I'm taking that rotated triangle and I'm sliding it up 6 and right 6 so that B prime is back on top of B, and that gives me that purple triangle. Now that's a rotated triangle, but now it is on top of B, so it was like it was rotated around point B. So to perform a rotation around a point other than the origin, you have to perform your rotation first, and then you have to slide the shape into position where you wanted your center of rotation to be. So those are the types of rotations around the origin, and then rotating around a point other than the origin. And then the second thing we want to talk about is something called rotational symmetry. And symmetry is like when you have a balance of things or a shape, or you have matching sides to a shape. But rotational symmetry is when a figure matches its original shape when rotated less than 60 degrees. In other words, if I rotate a shape, will it ever repeat its original shape if I rotate it one full turn? So like this triangle right here, if I rotate it, boom, right there, it looks like it's original. It looks like it's original, and we're back to where we were originally. So 3 times this triangle looks like it did in one full rotation. So it repeats every 120 degrees, or 3 times in a 360 degree turn, or 360 divided by 3. This pentagon, this regular pentagon, will repeat itself 5 times in one rotation. That's 1, 2, 3, 4, 5 times in one rotation. So it repeats every 72 degrees, or 360 divided by 5. This rectangle will repeat twice in one full rotation. Once, twice. So it has rotational symmetry every 180 degrees, or 360 divided by 2. That's rotational symmetry. Does this shape, does this snowflake have rotational symmetry? If so, what is the angle of rotation? So how many times does this repeat if it repeats? Well, if we rotate this, we see that it repeats once, twice, 3 times, 4 times, 5 times, 6 times in one full rotation. So it does have rotational symmetry, and it repeats every 60 degrees. So its angle of rotation is once every 60 degrees. Does this shape have rotational symmetry? If so, what is the angle of rotation? Well, if we rotate this shape one full turn, you'll notice it never looks like the original check mark. So this does not have rotational symmetry. So that's rotational symmetry and rotating figures as a transformation on the coordinate plane.